get going if you got any questions from anything we've done so far. Almost there. Okay. We had just finished example 2, and we're moving on to example 3. Okay. All right. Now, example 3, they do not show, and it's one of the more major examples, and yet they don't have it in the PowerPoint, so we'll have to do it ourselves. Okay. Any questions? Anything we've covered so far? I've gotten at least one quiz in so far. Very good. And by the way, I've gotten 3 papers in. Not bad, but could be more. So please try to get your stuff in sooner rather than later. Okay? No questions? Example 3. Page 70. Compare the graph of each of the following functions, there's 3 of them, with the graph of f of x is equal to the square root of x. So here's the function we're comparing with. F of x is equal to the square root of x. I think I started to draw the axes last time, and that's about all I got done. Okay? Y'all may have given me a few points. I don't remember. Seems like maybe you did. Okay. Okay. There's our axes. I want to plot, because we're going to be comparing it to it, this function, f of x, this one, not the one up there. F of x is equal to the square root of x. Can someone give me a few points there on how to graph this? Second? Okay, when x is 1, what's your y, or f of x? Did you say 1? Yeah, very good. 1, 1 is on that graph. Got it? Next. Say again. 4, when x is 4, what's the y? 2, excellent. I think we did this last time, didn't we? Or, yeah, okay. Give me a few more. No, 8. Did someone say that? Huh? 16 would be fine. I don't have room for it, but say again? How about 9? I like 9 better. Okay, okay. 4, 5, 6, 7, 8, and I got room for 9. And what's that answer? 3. 8 was a perfectly good input, but it's a miserable, irrational number that I have to plot, and, you know, I'd just be guessing at that. I'm guessing at a lot of this. You've left off my favorite. 0, and what's that? 0. Okay, what we have here is half of a sleeping parabola. Okay, we've seen that before. F of x is equal to the square root of x. Now, we want to compare with that these functions. G. Gee whiz, what color would you like it? Pick a color. Huh? What? Blue? Is that what you said? Okay, light or dark? Light. Okay, she likes light blue. Carolina blue here. Okay. So this one is g of x is equal to minus the square root of x. Can y'all see that okay? Is that showing up well? Yeah, it's okay. Okay, how do we plot that? What does this represent? Okay, you're negating all of the square roots, which are your y's. So what is this going to be? A reflection across the x-axis. If you negate 0, you get 0. Negate 1 up here, you get minus 1. See, the x's stay the same. It's the y's are negated. I'm talking negate. No, I'm sorry. Here is, I know you're in here. Just got to find you. Tyler, there you are. Tyrell, I can't read. Tyrell. Okay, got it. All right. So When x is 4, you're negative 2. Everything gets reflected across the x-axis. And up here at 3, it reflects down to negative 3 at 9. And there's the graph of G. Ha! That makes a nice little parabola. It's sleeping now. But it's two different functions, not one function. Okay. Does that make sense? Everybody see what we did? All right. The next one is h of x. What color do you want h to be? Pick a color. Red. Okay, I thought I heard a red before. Okay, your h of x is equal to the square root of negative x. All right, what is going on here? Can you do that? Can you take a square root of a negative? Not a negative number, but you can of a negative variable, because a variable could have been itself negative, and when you negate that, it becomes positive, right? So what is this one doing? Say again? These are going to the right. Is that what you meant, Seth? I can't hear well. Oh, okay. Reflect them across the y-axis. 0, 0 is still going to be the same. But when you do, you can't put in a 1 now, because that would give you a negative 1. You can't take the square root of that. But you can now put in a negative 1, because the negative of negative 1 is positive 1. So that's right up here. All right. And I know this is Justin. And something else. Huh? Embry, okay. Just getting to that, but I hadn't quite gotten far enough down the list. Okay, has anyone else come in that I didn't mark you down? Okay. So we're doing example 3, top of page 70 in section 1.7. Okay. I'm just going to guess here. This is Allison and Alexis. Am I right? I just don't know who this is. Okay, so sorry about that. Okay. All right. Anyone else come in since I called roll? Again, we're at example 3, top of page 70. We've plotted the reference function, which is square root of x, in dark blue. We did g of x, a part, in light blue, and we're just in the process of doing h of x, which is square root of minus x, in red. We got the first 2 points plotted, but what we're doing is every x that you have here, you're reflecting across the y-axis, so the x's become negative, but the y's stay the same. So this x equal 4, y is equal 2 becomes x equal negative 4, y is equal to 2. X equal 9, y is equal to 3 becomes x equal minus 9. That's minus 4, 5, 6, 7, 8, 9. Just made it under the wire here. And there's your positive 3, if I could get it right. There it goes. So here is that function. Okay? So you see that's reflected across the y-axis. Okay? One more to go, and this is our k of x. Any choice of colors here? Green. Light or dark? Dark, okay? Dark green. Okay, and here's your k of x is equal to minus the square root of x plus 2. The negative, the square root of x plus 2. All right? Now, what do you reckon you're going to do with that? Second? It's going to be flipped across the the x-axis, you're right, okay? But also what? Okay, what is the 2 adjusting here? To the left, because it's adjusting the x. X is on the horizontal axis, so it's a horizontal shift. But remember, anything to do with the x's goes in the opposite direction. So sure enough, the X it shifts to the left. So we're flipping and shifting at the same time, or separately. You can do it either way. So this 0 here, since it's the Y that's being flipped, it stays 0, but shifts to the left 2 places. Okay? Always go back to your original function. Okay? The 1, 1 flips over and becomes a -1, but shifts to the left 2 places. Is that right? No. Okay. Yeah, that's exactly what we need to be doing. I was trying to, yeah. And then that's it exactly. It's exactly shifting g of x 2 places. Okay? So that sure enough, that was what it was coming out to be. I wanted to make sure I was doing it right. Yeah, that shifts 2 places to the left, but the whole graph gets shifted. So this one gets shifted 2 places to the left, right there. In other words, this one's reflected and shifted. So that's exactly what we're doing here. And this one gets reflected and shifted 2 places to the left. So here is your K function. Okay? Just like G, only shifted 2 places to the left. Perfect. Okay? Does that make sense? All right? Any questions on it? So, the book sort of, and this one, it didn't matter. And that's what one of the things I was debating. You could have shifted the whole function, the F function, to the left 2 first, and then flipped it. You get the same thing. In other words, you shift this one to the left, and then flip it, and you get the same thing. Or shift this one, which is already flipped, to the left, and you got this thing. You flip it first, and then shift. Some of them, it's a little, I'm hesitant to do them out of a certain order. This one, it didn't matter. Okay? We'll save those for the quizzes and tests. No, I'm just kidding. Okay. Sort of. Okay. Any questions on example 3? Covering a lot of stuff there. Okay? Now, there is a checkpoint. I suggest, especially if this was a little new to you or hairy to you or not completely clear to you, as soon as you have an opportunity, do your checkpoint. Okay? Now we're ready for that next. Anyone need that up there a little longer? Okay. Okay. Everybody got it? Oh, still got it. All right. No, now, while I'm waiting here, did everyone get a copy of the first quiz? Did anyone not get it? You did not. Okay. Let me see if I can find that. I just happened to think. Okay. Do you need graph paper? Okay. I think that may be everybody. I took a lot of quizzes, but I can make them. All right. Now, technically, remember, we finished 1.6 last time, so technically the quizzes are due next Tuesday. If you need more time, you can have it, but don't drag it out. Please get them in sooner rather than later, because the sooner you get them in, the sooner I can grade them. You can see if you missed anything. I've had people turn in the quiz on the day of the test, because you got to turn in the quiz before you can take the test or get a 0 on the quiz. I don't like to give 0s on quizzes, so you have to ask me to do that. But I've had people turn it in the same day of the test, And then when I grade the test, they made the same error they did on the quiz because they didn't give themselves any opportunity for me to give them feedback because they didn't turn in the quiz until the day of the test. Please get them in sooner so I can get them graded. You can see if you missed anything, what you missed, so you don't make the same mistake again. Okay? All right. So let's move on to the comments on example 3, and we'll get those in a second when it finishes doing this. I wrote on that page here. When sketching the graphs of functions involving square roots, which we're just doing, remember that you must restrict the domain to exclude negative numbers inside the radical. Okay? So if you think about this, what's inside the radical? On this one, x. So x must be, another way to say non-negative is? Okay, positive, very good. But mathematically, greater than or equal to 0. That's what it means not to be negative. You're only looking at numbers greater than or equal to 0. But if you have a minus x in there, that means your x's now have to be negative, because when you get negate a negative, it becomes positive, and you have to have what's in there positive. So now your x's have to be less than or equal to 0. 0 would be fine too. How about this one? What is the requirement here? What's inside the radical has to be greater than or equal to 0. What's inside the radical now is x plus 2. Let's go back to dark. Okay, x plus 2. That's inside the radical has to be non-negative, greater than or equal to 0. Solve that inequality. How do you do that? Subtract 2 from both sides of the inequality. And adding or subtracting positive or negative numbers from an inequality, a directional inequality, doesn't change the direction. It's only when you multiply or divide negative numbers that flips the inequality. Multiplying or dividing positive numbers leaves it the same. But we're not multiplying or dividing. We're subtracting. No sweat. This gives us x is greater than or equal to negative 2. And that's exactly what you get there. So always, what's inside the radical, say it has to be greater than or equal to 0. So this one here, negative x has to be greater than or equal to 0. You cannot take the square root of a negative number. So what's in the radical has to be positive, or 0. But now, to do that one, what do we do? To solve that for x, I don't care what negative x is, I need to know what x is. Divide or multiply by minus 1, so that's going to change this sign. Change the sign of 0 too, but that doesn't have a sign. But what else does it do? Flips it, so that makes x less than or equal to 0. Okay, so I really shouldn't have put that yet, but I was just illustrating it. So that statement's not true, but that one is. All right. Any questions on that? What's under the radical has to be greater than or equal to 0. Always. Okay? Any questions? Got it? All right. Up till now, we've been doing transformations, and if you go back and look at our graphs here, once you got this shape here, that shape doesn't change. Same shape, it's just flipped, or flipped and shifted, or shifted and flipped. But the shape remains the same. Okay? Now, what we're going to move to next, and we call those rigid transformation. That shape stays the same. It moves around, but it stays the same. Now we're going to go to non-rigid transformations. And those are usually of two types. You're either stretching or shrinking. Stretching or shrinking. But the shape changes. It gets altered. Okay? Like going into a house of mirrors. Your shape gets all sorts of weird distortions. So we're not going to be that bad, but we will be changing. Okay? All right. So non-rigid transformations. What does this entail? Well, horizontal shifts, vertical shifts, reflections are all rigid transformations because the basic shape of the graph is not changed. Now, how do we get horizontal shifts? How do we get horizontal shifts? We had one back here. This one. Let me get this other stuff off of there. Okay. This was a horizontal shift. How did we get it? See, this one shifted over here. How do we get that? Adding or subtracting from the x, the horizontal variable. Okay? We didn't have any vertical shifts there, but we've had some before. How do we get vertical shifts? Got horizontal shifts by adding or subtracting from the horizontal variable. So a vertical shift you get by adding or subtracting from the vertical variable, which is usually y. And what is y? Your f of x, your function, exactly. Okay? Reflections, how do we get reflections? Negating. Okay, well, you negated the x and you flipped across the y-axis. Negate the y, you flip across the x-axis, right? So, well, what is negating? It's sort of like subtracting, isn't it? Not quite similar. So, how in the world are we going to get non-rigid transformation? What two operations have we left out? Multiplying and dividing, you're absolutely right. These transformations change only the position of the graph in the coordinate plane. Flip it, shift it, you move it up and down, wherever. But non-rigid transformations are those that cause a distortion, a change in the shape, which, like I said before, are either stretches, shrinks, vertically, or stretches or shrinks horizontally. Okay? Still getting? Okay. Now, for instance, a non-rigid transformation of this one, y is equal to f of x, is represented by g of x, which guess what? Not adding or subtracting anything, you're multiplying some constant c times your f of x. All right, let's think of what that's going to do. F of x is your y value. You're multiplying it by c. So let's say c was a big number, like greater than 1. So what are you doing? Stretching, a vertical stretch. Okay? But what if c was a number less than 1? Okay, let me say that. Between 0 and 1. Now you're taking a fraction of it, it's a vertical shrink. Now why did I say between 0 and 1? If I just said less than 1, you're going to go negative. But what is a negative? It's a reflection. Okay, so don't confuse this. This is greater than 1 or between 0 and 1. Those are the things. So it's a vertical stretch when c is greater than 1, a vertical shrink when c is between 0 and 1. Now, if you have a minus on either one of those, that's also a reflection, which we'll do some of those later. Okay? Another non-rigid transformation of y is equal to f of x. Guess what we're going to do this time? I'm not going to multiply by the y by the c, but we'll multiply the x by the c. What's that going to do? Horizontal stretch or horizontal shrink? Okay, now you tell me. A number greater than 1 is going to do what? Say again? Okay, so what are we messing with? The x's. And remember, everything that deals with x's is backwards from the y's. So a c greater than 1 is actually a shrink, and a c between 0 and 1 is actually a stretch. Oh man, those x's are so pesky, aren't they? Represented by h of x equals f of cx. Now you're multiplying your independent variable, your horizontal variable, by the constant, and that transformation is a horizontal shrink when c is greater than 1, backwards, and a horizontal stretch when c is between 0 and 1. Strange but true. Everything you do to the x's is backwards from what it is to the y's. Okay? Remember that? Okay. Everybody got it? Now, let's do example 4. Compare the graph of each of these functions with the graph of f of x is equal to absolute value of x. So the first thing we're going to do is plot f of x equal absolute value of x. Okay? Let's tick off some points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't need that many. 1, 2, 3, 4, 6, 7, 8, 9, 10. 1, 2, 3, 4, 6, 7, 8, 9, 10. Don't need any down there, but I'll put a few just to be fair about it. Let's plot f of x equal absolute value of x. Anyone remember how this looks? V-shaped. Okay? What we do, this is a piecewise defined function. I don't know if you realize that, but this is what it is. Remember, that is simply x if x is what? The absolute value of x is the same as x when x is positive, because that's why absolute value means always positive. So that's, let's put it greater than or equal to 0. That's how we say positive. We don't have to write all those letters. Math is so concise, isn't it? But what is it if x is negative? Say if x was a negative 3. What is the absolute value of negative 3? 3, how did you get that? Negate the negative 3, right? Because negative 3 is positive 3. So that's minus x, and that's if x is less than. You could put equal to, but since I already put it, I'll just put it there. Less than 0. That's how we do absolute value. You may not have ever thought about it that way, but that's what it is. So let's take that first one. F of x is equal to x for all positive x's. What function does that look like? In fact, it's exactly the same. F of x equal x. We had a name for it. Oh, it's so long ago. It must have been last Thursday. Okay. Long time passing. All this builds on itself. What function is that called? Okay, give me some points. Give me some points. 0, 0. Give me another point. 1, what? 1, 1. Another one. 3, 3. Okay, jumping way up there. My graph is not good. You see what's happening? That's the diagonal line. We call that the identity function. That's f of x equal x. The y is equal to x. So the y value is same as the x value. But what happens if we go negative? Say again? Okay, the opposite of x. In other words, your slope here was what? 1. Oh, y'all are good, okay? And what's your slope here? Negative 1. So it's the same thing, but it's a negative. So this is this diagonal. Like you said, it's the V shape. There is absolute value of x. Okay? Now, what you think's going to happen if I multiply and do, okay, what color you want h of x? You choose. Second? I can't hear. Bling. Okay. I heard green, I guess. Okay, so let's go with bling. Okay. Blue and green. Okay. That means money. I don't know. Okay. What is going to happen with h of x? H of x is going to be the green. What are you doing here? Multiplying your y by 3. So when the y is 0, like it is here, 3 times 0 is 0. Here, when the y is 1, it becomes 3, right? When y is 2, right here, it becomes 6, isn't it? Up here, okay? When y is 3, it becomes 9. Let's see, 6, 7, 8, 9, somewhere up there, okay? I don't have it too well, but that's what it is. Now, rather than a slope of 1, it's a slope of 3. And guess what happens on the other side? Same thing. When y is 1, it becomes 3. When y is 2, when y was 2 here, I don't have these drawn very well, it becomes 6. And when y was 9 here, it becomes, 3 here, it becomes 9 there. Okay? Something like that. Here is now, phew, goodness, that's an ugly line. That is your other half of the V. That's not much better, but I'll erase that first one. That's really bad. Okay? It's still a V. It's just a steeper V. Okay, you might say, isn't that a horizontal shrink? No. It's a vertical stretch. You tied it. Remember those little toys? You had the strings to them, and you pulled the string up, and the arms go up. That's what's happening here. You pull up, and this thing goes like this. Vertical stretch. All right, what happens to G of X? What color you want G to be? Orange. Creative here, okay? Now, yeah. What is G of X? 1/3 of absolute value of X. And you're taking 1/3 of the Y value, so 1/3 of 0 is still 0, but 1/3 of 1 is now 1/3. 1/3 of 2 is 2/3. 1/3 of 3 is 1. 1/3 of 4 is 4/3, which is 1 1/3. 1/3 of 5 is 5/3. 1/3 of 6 is 2. 1/3 of 7 would be 7/3, which is 2 1/3. Okay, you see the pattern? 1/3 of 9 would be that. So it's not a very straight looking line, but there's what you got. What is it? The elephant sat on it, right? It's a vertical shrink. Okay? You squished it. You forced it down. What happens on the other side? Same thing. 1/3, 2/3, 1, 1 1/3, 1 2/3, 2, 2 1/3, 2 2/3, 3, and so on. Okay? So there's your, both sides got shrunk. Okay? Vertically shrunk. Does that make sense? Got it? Getting it? Okay. Do you think it's going to help to see what they do to it? I can't imagine they can draw a better picture. Can you? The answer is no, folks. Okay. Let's see. Relative to the graph of y is equal, alpha of x equal absolute value of x, the gray line there, the A part is h of x is equal to 3 times the absolute value of x, or 3 times alpha of x. So that's a vertical stretch, and you stretch that absolute value function up. See, you distorted the shape. The shape is no longer this V, it's a steeper V because you stretched it up. Okay? 3 times 0 is still 0, so you didn't stretch that one, but all the rest of them you stretched upward. That's what it gives you. Make sense? Okay? The second one, similarly, the graph G of x is 1/3 absolute value of x, which is 1/3 f of x. Vertical shrink, each y value is multiplied by 1/3, reduced by 3, a factor of 3, multiplied by 1/3. So that is going to, here's again your parent function, f of x equals absolute value of x, and now you shrunk it, and every one of these is 1/3 as high as the previous. Make sense? That's a vertical shrink. Okay? Any questions? That's the last slide they show. However, there's another example here. Why they left off the ones that I think are probably the most important, in other words, sort of the toughest ones. So let me go back to black for a moment here. Not black, it's really dark blue. Okay. Example 5 says, compare the graph of each function with the graph of f of x is equal to 2 minus x cubed. Oh my goodness, 2 minus x cubed. Not any parent function I can remember, so we're going to have to figure out how to plot this one. There's actually 2 or 3 different ways to do it. How would you go about plotting that one? I give it to you on the test. What's going to be your first approach? Plug it in, plug it in. Good old Glade, right? So let's set up a table, a t-table, or whatever you call it, x, f of x. But remember the f of x is 2 minus x cubed. Okay? So give me an x. 1. I don't think so. Oh, you mean another x is 0? Okay, yeah. Okay, I'll put okay. Okay. For x equal 1, what is your f of x? 1. Okay. For x equals 0, what's your f of x? 2. Okay, give me another x. Say again? 2. Okay. What's your f of x? A little louder. Is that a negative 6? Yeah, negative 6. Got it? Give me another x. Negative 1. What does that produce? 3? Very good. Everybody see that? Anyone not knowing how we're getting these numbers? We're pulling them out of the air or some obnoxious body part. Never mind. Give me another x. Did I hear a negative 2? Okay, let's do negative 2. What would that be? 10. Okay. I'm guessing we probably can't do many more. So let's see what we got. Let's do our axes. We're going to need plus and minus. Okay, and we need plus and minus above and below. So let's see what we got. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Not going to need anywhere near that or this. But let's put them out here. We will need several here. Okay, and down here. Ooh, didn't plan this too well, did I? Let's plot that first point. One, 1. 0, 2. 2, negative 6 is somewhere way down there. Okay, probably don't quite have it right, but somewhere down there. Negative 1, 3. Negative 2, 10. Somewhere way up there. Okay, now, isn't this looking sort of familiar? Coming down real steeply here and then sort of flattening and doing that. Yeah, that sort of looks like a cubic function, doesn't it? What's different about it? You've negated the cube, which means you flip that across the y-axis. So usually your cubic function does like this. When you flip it, it's doing like this, and then you move that up too. Yeah, that makes sense. That's the other way we could have graphed it, by the way. So anyway, that's our parent function. All right. What we're going to do next is you give me a color. Say again? Baby blue. I knew she was going to say that if I'd have thought about it too deeply. Okay, baby blue. And here's going to be our g of x. G of x is f of 2x. G of x is equal to f of 2x. I'm sorry? Okay, is start with your parent function, x cubed, which would be, you know how that goes, like that. Then negate it, because that's the next thing you do to it, which flips it over, which then has it doing like this, and then move up to it. And that's exactly what you got, right? Either way. So f of 2x. Hey, what are we doing here? Anyone want to give me a suggestion? What is this called? First, what direction? Is this horizontal or vertical? Horizontal, because you're messing with the x's, the horizontal variable. And what's it doing to it? Stretching or shrinking? Shrinking, because it's an x, it's backwards. So what you're going to do is take every x and divide it in 2. Well, half of 0 is still 0, right? That's your x value there. Half of 1 is 1/2. Half of, at 2 it was -6, so that's going to, I'm sorry, at 1 will be -6. So that one's going to be right over here, okay? Up here, this was a -1, half of that is -1/2, and up here where it was -210, half of -2 is -110. So you're somewhere up there. So here's what you've done. You've still got a little bit of a jiggle there, but you've done a horizontal shrink. Squeeze that thing in from side to side. Okay? What color you want H to be? Red. Okay? Good. All right. Red, the H is going to be f of 1/2 x. Okay, tell me what you think is happening here. First, give me a direction. Okay, I saw the hands go. Okay, horizontal. Horizontal what? Second, stretch. Exactly, because this C here is between 0 and 1. So that is a stretch. So every x now gets doubled. Well, double 0, you're still 0. Double this 1, you're at 2. Double this -1, you're at -2. Double this 2, you're at 4. Okay? And double this -2, you're at, whoops, 4. I went to 3. Okay? So here's what's happening, folks. Same general shape, except Yolanda's here, and except it's a horizontal stretch. Okay? So you get that cubic shape here, but you get it stretched horizontally. Does that make sense? No. Okay, what's... Oh, I see. Okay. All right. Good deal. That was example 5, the last example in section 1.7, which means there's a checkpoint right after it, and since this seemed like I had to pull a few more teeth to get answers here, I would highly recommend you do the checkpoint shortly after. And if you look in the book, you see their graph looks almost as pretty as ours. The colors aren't nearly as right, but you know, they look similar. Any questions on that? All right, let's do vocabulary. Top of page 72. Okay? In the first 3 exercises, fill in the blank. Horizontal shifts, vertical shifts, and reflections are called blank transformations. What? Okay? Shifts and reflections are rigid. They're the rigid ones, okay? Number 2, a reflection in the x-axis of y is equal to f of x is represented by h of x is equal to blank. Reflection in the x-axis. H of x would be what? Minus f of x, okay? You're negating the y to give a reflection across the x. Very good. While a reflection in the y-axis of y is equal to f of x will be represented by h of x equal Yeah, f of minus x. F of minus x. You negate the x. Very good. Number 3. A non-rigid transformation of y is equal to f of x represented by g of x equals c times f of x is a blank blank when c is greater than 1. I'll give you a hint. The first blank is a direction, the second blank is a... Say again? Vertical stretch, exactly. When c is greater than 1, and a blank blank when 0 is less than c is less than 1. In other words, c is between 0 and 1. It's a vertical, no, okay. The c is still changing the y, so it's still vertical, but what's it doing now? Shrink, exactly, okay. So your c has to shift, c has to move and start working on the x to be a horizontal. If it's on the f or the y, that's a vertical, okay. Number 4, matching. Match the rigid transformation of y is equal to f of x with the correct representation of the graph of h, where c is now c is positive. Okay, we're not worried about verticals. These are all rigid transformations. Not worried about non-rigid. These are all rigid. So h of x is equal to f of x plus c. What is that called? H of x is called equal to f of x plus c. You're adding to the f, which is the vertical shift up. Okay, yeah, vertical shift up, and that looks like that's going to be number 4, our IV4. Okay, vertical shift of f, c units up. Okay, B, h of x is equal to f of x minus c. Okay, as a vertical shift down, that looks like Roman numeral 2 little I. Okay, h of x is equal to f of x plus c. Now the c is added to the x. What kind of thing is that? Horizontal shift left. You got it. Okay, and h of x is, and by the way, that's Roman numeral 3 little 3I. And then D is h of x is equal to f of x minus c in parentheses, horizontal shift right, which is the Roman numeral little 1. Okay, homework exercises here. Either 5 or 7 or both. Do number 9. It has, what's that, 7 parts? Okay, do number 9. Do either 11 or 13 or both. Any of the odds 15 to 19, those are fun, okay? All of them are fun, okay? Any of the odds 21 to 45. Now, notice what you're doing here. 21 to 45, they've given you a function, and you identify first the parent function, and then the sequence of transformations to go from f to g. They give you the parent function. No, you identify the parent function. Okay, then the next group, 47 to 53, the odds 47 to 53, they do the words, you write the equation. So you see the top part there, 21 to 45, does equation to words, and 47 to 53, do words to equations. Okay, so one does one way and one does the other. Get used to those. Just looking into the crystal ball, think you'll see something like that again. But I may be wrong. Okay, now number 55 or 57 or both. Any of the odds 59 to 63. Do either 65 or 67 or both. and then do 69. That's the only applied problem they have here. But under exploration, not a bad idea to think through those two true false that you have, 71 and 73. Make sure you understand why they're either true or false. And then 75, 77, 79, not a bad idea to read through and think through those issues. Any questions? Section 1.7. All right. If not, let's go to 1.8. All right. Takes just a while for this to go through its gyrations. Got to wake up again, and PowerPoint has to go through all its things again. But it's going rather a little more quickly this time. All right, we will now do the slideshow through from the current slide. All right, still doing functions in their graphs. Have you got the idea they like graphs in this book? Okay. We'll now look at combinations of functions, and one other. Some of these are things that will make, I think, a lot of sense to you. Then the next one is going to be a composite functions, which I'm not sure that you've done before. Maybe you have, but it's sort of a new concept. Guess what? We're going combinations of functions. We're going to add functions, subtract functions, multiply and divide functions. That should be pretty easy, don't you think? But then the next part, I don't know if you've done before, find the composition of one function with another. Kind of a new concept here, but it's pretty straightforward. And then we'll use combinations and compositions of functions to model and solve some real-life type problems. That's where it's fun, right? All of it's fun. So let's start with the arithmetic combination of functions. Those four operations are arithmetic operations, combinations, adding, subtracting, multiplying, and dividing. Just as two real numbers can be combined by adding, subtracting, multiplying, dividing. You got those down pretty well. To form other real numbers, so two functions can be combined to create brand new functions. Okay? For example, if you had the function f of x given by 2x minus 3. Pretty simple. What kind of function would we call that? A linear function. Very good. And this g of x, which is x squared minus 1, what would you call that? That's a quadratic function. Very good. They can be combined to form the sum, the difference, the product, or the quotient of f and g. Now, the first three of those, sums, differences, and products, no sweat, because these are polynomial functions. You've already identified that. You can always add, subtract, or multiply any two polynomial functions together. You're going to get a polynomial function. However, when we do a quotient, what do we have? No longer a polynomial. What do you have to watch for if it's a quotient? What is the bothersome thing about a quotient? Yes, that denominator can't be 0. So if you're dividing by g, say for instance, you have to make sure that g can never be 0. So you have to exclude a couple of values from the domain because they just won't work. So let's first start with the sum function. They're taking away my fury here, okay? F of x is 2x minus 3, and g of x is x squared minus 1. So when you do f of x plus g of x, you just take f of x and add to it g of x. That's all. Except, okay, now, notice what they did here. Part of this, most of this is just to emphasize. They put parentheses here so you can tell what f of x was, and then they put the plus sign, and then they put parentheses around the g of x. Actually, in this situation, those parentheses do no good at all, except just to emphasize what's f and what's g. Because when you have a parenthesis that leads off an expression, and there's nothing around that parentheses, you can just delete it. If you have a parenthesis that follows directly after a plus sign, with nothing else on either side of it, you can delete that too. And then all you have to do is combine like terms. What like terms do you see? Okay. Only the constants. The x squared doesn't have like terms, so write it down. The 2x doesn't have a like term, write it down. It's a plus because nothing's in front of it. But these two are like terms, so you combine those, and that gives you -4. Wow. I wish I could make that harder, but I can't figure out any way to do so. I mean, it's just so simple, right? Add the two functions together. Now, you think we can subtract those two functions? Let's do it before they show us how. You tell me how to subtract the two functions. And by the way, I hope you realize difference means subtract, right? Okay. All right. So let's do f of x minus g of x. I don't want you to watch them do it. I want you to do it yourself. What would that be? Okay, that would be the 2x minus 3. I can't read. I'll put it in parentheses too because they did. Okay, if this is a difference, it's a minus x squared minus 1. Now, did I just put that parentheses there for convenience? No! With the minus sign, that is absolutely essential you put the parentheses. Here, it was optional. Just make it look better so you identify f and g. With the minus, you got to put. I didn't need this set of parentheses. I had to have that. But yes, because it negates everything inside. So that's the first thing we're going to do. Remove parentheses. So what's the first term? 2x minus 3 minus x squared plus 1. You got it. Don't forget that last one in there. Negate everything inside. How would you rewrite this? Negative x squared plus 2x minus 2. You got it. All right. Let's see if they did it right. Look at them. They got it right. Negative x squared plus 2x minus 2. That was so much fun. Let's go back and do it again with the product. Okay? So the product is going to give us f of x times g of x. What would that be? That would be 2x minus 3 times x squared minus 1. Okay, how do you do this? Curses fold again, okay? So let's do that. 2x cubed minus 2x minus 3x squared plus 3. And now we combine like terms, but there aren't any. Just rearrange them maybe. What would that be? 2x cubed minus 3x squared minus 2x plus 3. Now, you didn't have to rearrange them, but usually we do write them in descending orders of powers. That's how you multiply two functions. And you get a smiley face in the process, right? Never mind. Okay. Sure enough, they got 2x cubed minus 3x squared minus 2x plus 3. Good for them. Okay? Think we can divide these two? That's what quotient means. What would that mean? The quotient of f and g. That means you put f on top. It's f of g over f of x over g of x. Okay. Thinking faster than writing. What would that come out being? 2x minus 3 over x squared minus 1. Guess what we can do now? I can't think of a thing. That's it. That's all, folks. Boy, wish I could make that harder, but okay. Well, there is something. Oh, boy. Okay, second. I can't hear. I can't hear. Multiply. What do you multiply? Okay, if the denominator had a denominator in it, yeah, is that what you mean? It doesn't. It's just that. That's all, folks. Okay, now your question here. Okay. Okay, these two. Now, what are you doing if you made that a positive? What would make that a positive? That's if you multiply numerator and denominator by -1. But you can only multiply things that are divided, and this thing is subtracted and that thing's subtracted. You can't simplify a subtraction by dividing or multiplying. Okay? So you don't, okay? You can't, don't give me canceling things out. Canceling is really division. You can't divide things that aren't multiplied. This is subtracted. You can't divide something out of something subtracted. You have to use the other. The only thing you have to watch for, and that's what we said earlier, what can't you do? Divide by 0. So now we have to say that denominator, whereas before it was no problem when you're adding, subtracting, multiplying, that could be 0, no sweat. But you can't ever divide by 0. So that denominator, x squared minus 1, cannot equal 0. How do we solve that? Factor it, and what does that factor as? X minus 1 times x plus 1. That product cannot equal 0. So therefore, neither one of those can be 0, right? So that means x minus 1 cannot equal 0. And, not or, and x plus 1 cannot equal 0. What does that tell you? The first one tell you. Solve for x, add 1 to both sides, and that says x cannot equal 1. Over here, that tells you you subtract 1 from both sides. That tells you x cannot equal -1. So you have to exclude those two values from the domain. Before this, the domain was all real numbers for everything. For your f, for your g, for your sum, for your difference, for your product, but not for the quotient. The quotient you had to say, whoops, can't include x equal +1 or -1. Other than that, all real numbers. Okay. And that's what they got to. Now, if there was something you could do, like factor something out, like if this was a 2x minus 2 up here, you could factor out a 2 and leave your x minus 1. This factor to be x plus 1 times x minus 1. Yeah, you can simplify that, but you can only divide out things that are multiplied. Those would be multiplied, those would be multiplied. You can divide there. This one wasn't. Nothing will divide into either of those or multiply by either of those, so leave it alone, but you do have to exclude plus or minus 1 from the domain. Make sense? All right. I've already introduced the concept of domain to you. So we are unfortunately out of time. Quit crying. Get over it. We'll be back Tuesday. So we're going to start with arithmetic combination there early in the page here. And there may not be lots of examples you can do. Let's just wait and do examples next time. You do have plenty for 1.7, and you got the quiz, right? Everybody's got a copy of the quiz, right? Anyone who doesn't? Okay. Then got plenty to work on this weekend. That should make the weekend just fly by and a lot of fun, okay? So have a good weekend. What's that? I'm not sure. What was it about?
About having to miss class.
I'm sorry?
It's about me having to miss class Monday.
Oh, Monday? We don't have class on this class.
Not Monday, it was for Tuesday, I'm sorry.
This coming Tuesday? Or next?
Past
Past Tuesday. Okay, now, I saw that you had sent one, but I didn't have a chance to read it. I didn't know.
It was just say, I rely on my mom on Tuesdays, Wednesdays, and Thursdays to come and watch my little one because my old lady, she goes to work at 6 o'clock.
Right.
You know, I got to be here at 8. So
Right.
like mom.
Right.
Sometimes she don't get there till 7:45.
Oh, wow. Yeah.
Sometimes she gets there earlier than that. But
Right.
Monday night, apparently, Monday, she had been sick and thrown out, so
Oh,
she had to come over and
Right.
give it to the baby.
Right. Well, that's why I record everything. Hopefully you can go back and watch it.
I need to, actually. Some of this stuff is just flying over my head.
Oh, okay. Well, ask questions.
We left at 1-4, so like y'all did, what, 5, 6, 7, and 8 today?
No. We finished, we were in 1.6 last Thursday. Not quite finished with it. Oh, okay.
That's what it is. I'm like, I'm missing something. But
Okay.
I'll go online.
Yeah, catch it. Okay. I'm sorry?
Did you get a chance to grade my report?
Yes, I did. I don't have it in Blackboard yet, but you did okay on it. I have it somewhere here. Let me turn off Screencast-O-Matic.